Good afternoon, everyone. My name is Srini Ambati, and I'm lead cloud solution architect at Microsoft. Um, I'm going to be practice for the session for Joel today, and this session is very interesting. Uh, you are going to hear a lot about this. As always, you can find the schedule, slides, and also recorded videos using the links that I'm going to provide in the chat window also that are here. So with that said, I'm going to introduce Joel. Joel, welcome. And Joel is CTO at Causeway Solutions. He is a technologist and he's from one of my favorite cities, New Orleans. Uh, thank you, Joel, for doing this presentation. And most important thing is you look like you love fun and spending time with your family. You're a amazing pool player. Love to see that all together, right?
I wish
So
I was
this
amazing. Yes.
uh, we can make out you love what you do. So definitely that's really good. Um, I also know New Orleans, how fun city that is. So really, really nice to see technologists from that area here presenting for us. Thanks, Joel, and I'll hand over the session to you. You can share your screen and continue.
All right. Thank you for that introduction, Srini. I will say, and there may be some folks here. I've been around the area presenting for a long time. Um, and my company is from New Orleans, which means I get to spend an inordinate amount of time down there. Um, but I actually live in Harrisonburg, Virginia, the home of James Madison University, which is about 2 hours southwest of Reston. So, um,
That's fine.
yeah, but no, I like New Orleans as well. Most of my coworkers are stationed down there too. Um, but it is a beautiful day here in the Shenandoah Valley, so I'm really happy that you all have come out for this virtual conference, and let's just jump right in. We're going to talk today about something that I've spent the last couple of years working on. I've been working around big data now since 2015 and really hands-on since 2017. I work for a really small company, Causeway Solutions, and we are a data analytics and prescriptive marketing firm. We do, we provide targeted marketing, we provide mailing lists, but with a high degree of intelligence, which means that we deal with uh, nationwide data across the United States. We're talking very, very wide, into the 7, 8, 900 column worth per row, effectively over all the adults in the United States. And we have a variety of different sources that provide that information. We keep in active profile hundreds of terabytes of data at any given time. And then we have some specific challenges around the frequent but irregular updates. And so most of our work is event driven as opposed to schedule driven, although we have a certain amount of that as well. And that means from a big data standpoint that these are the kinds of issues that we're concerned with. We have a constant stream of ingestion. Time to market for us means the amount of time that it takes for that data to come in and get into our analytics pipelines. And that's something that has to happen very quickly so that we can begin processing and running analytics. And we have a great many machine learning pipelines that also get run against this data, against all of those records, both event driven from the fact that there are new records present, and on demand driven from specific tasks that our analysts have. We have to merge the new data coming in. We have to purge old data that doesn't exist anymore. We do a certain amount of matching against data source to data source, and all of this work is constant. It's just this constant churn, and it literally results in tens of thousands of data factory pipeline runs every year. Now, I don't know what situation obviously our attendees are in, and that may not sound impressive to them. But considering that we are a company of 10 people with really only one dedicated technologist and myself, the fact that we're able to do all of that by leveraging the features that are available in Azure and in Data Factory and Logic Apps and Function Apps and some of these things we're going to talk about today, I find that really impressive, and it's kind of given me a new interest in doing cloud-based work, right, and building these processes and systems. And so I spend most of my time enabling all of this great work, and the only way that that's possible is through automation. And so automation is my primary focus. Now, those tens of thousands of runs are literal pipeline runs. So the three things that we're really going to talk about today, and we're going to focus our efforts on the tooling that I have built. And so this is an example. We're going to walk through some of the examples that I've built to solve this problem for our very small company. But the concepts are actually what's important. So whether you try to replicate the way that the instance, the way that I've done it or not, doesn't really matter. What matters is that you take the concepts away. So I hope that this will provide that for you. In today's terminology, pipelines are the actual Azure Data Factory pipelines. So those are the ETL workloads. And I've spoken before with other folks about sort of my approaches to pipelines, and I won't go into those details except to share with you that I try to make my pipelines very granular. We'll talk about that a little bit on the next slide. And then triggers are the events that drive those workloads. So what causes a workload or a pipeline to execute? Data Factory itself supports a number of different triggers. So depending on the complexity of your scenario, that may be sufficient for you. My assumption, however, is if you're interested in this topic, that you're discovering that relying on the built-in triggers it becomes very brittle over time, and also might not necessarily meet all of the particular needs that you have. And that's where queues come in. So the queue, the thing that we're going to be talking about building today, doesn't actually exist in the context of Azure or Data Factory. It's something that we have to build to externally manage pipelines and triggers. So you can get a lot of automation out of the built-in tools, but you'll find very quickly that at a certain certain throughput, that it's just not sufficient, and that's really what is driving this topic today. So just a quick couple thoughts on pipelines, and we're not gonna spend a whole lot of time on this. But a pipeline should be designed in isolation, and what I mean by that is that it should be a granular approach. A pipeline should basically try to solve a single problem or accomplish a single task, and I don't mean that. Please don't take away that means that the pipeline needs to be simple. A pipeline can still have many activities because it may take many activities to express that task that you're trying to accomplish. From a simple ETL perspective, that task may be connect to an SFTP server and download the latest files based on a certain date range to, say, a blob store. And that task alone is, in my mind, about as complicated as the pipeline should be. Now, I mentioned earlier that we end up running tens of thousands of pipelines, and this is one of the reasons for that, because I designed these very small, isolated, granular driven pipelines. And then when this pipeline runs, I don't also mean to say that that's all that can happen. What frequently happens is, okay, great, I've downloaded those files, I've got them in blob storage. Now what needs to happen? Okay, well, now I need to run them through an ETL process. Now, I could do that in the same pipeline, but I'm starting now to build a larger chain of activities. And the larger that chain becomes, the more brittle the solution is. And I've been dealing with Azure Cloud since its inception. And one of the very early first lessons that has always stuck with me is that you don't design for if something will fail, you design for when something will fail. And so that's part of what this idempotency is about. That is that I should be able to rerun the pipeline over and over. So if I encounter an error in my pipeline, I should be able to run it again. And if I run it multiple times, I should get the same result. That is largely a design choice. It's not necessary for this automated pipeline thing, but it certainly makes the automation simpler because when I need to re-execute tasks, I have a faith and confidence that the result is going to be consistent. But so back to my point about subsequent pipelines, I would rather have a pipeline do its one task, its primary task, and then trigger another pipeline run to handle whatever that next task is. And so, we have processes that may chain together 4 or 5 pipelines, and that's the end-to-end ETL process, but each one of them is an independent agent. So again, they're designed in isolation to just do their task. Back to error handling, that also means that if I have 5 pipelines chained together and everything's fine up until the 4th one, I can go back into this queue system that we're going to be discussing, and I can fix my problem, or maybe there's not even a problem. Sometimes servers just fail. Sometimes the resources that I'm accessing in Azure go down, and just if I just run the thing again, then it succeeds. So for whatever reason it failed at step 4. Well, I don't actually have to go back now and rerun 1, 2, and 3. I can just pick up right at number 4. Again, over the past few years of dealing with this day in and day out at this really high level of throughput, those little features have become super valuable to us. So let's take a minute and talk about triggers, because triggers are, of course, the things that cause our pipelines to run. And they're kind of, I've broken it down into what I think of as natural triggers and artificial triggers. Natural triggers are responses to something happening. In the case of Data Factory itself, those options are really limited. Those trigger options are really limited. You have scheduled runs, which is a reaction to the clock hitting a certain time, right? So that's a natural trigger. And then you have events, and in Data Factory, those events are limited to blob storage events. So that, so if you create a blob, if a blob gets created in a container, and by the way, the creation, the created nomenclature is slightly misleading, just by the nature of blobs. If you have an existing blob and that blob gets updated, it doesn't actually happen. It gets destroyed and recreated. So it may be a pre-existing blob or a blob with a name of another blob that was already there, the same name. But when you hear created, you can think created or updated. It's not technically accurate, but semantically it achieves the purpose. So event triggers are also really important, because and that's where we got started in this whole Data Factory automated triggering. We got started by wanting to react to new blobs showing up, because we very heavily leverage blob storage. And for us, most of the time, these triggers occur when a new blob shows up. So those two natural triggers, they make a lot of sense, and they get relied on extensively. And then there are the artificial triggers, which are manual. And so an artificial trigger is where it's not based on an event. It's just I have decided, or some process has decided, this pipeline needs to run. And so you can go into Data Factory and click the Trigger Now button. And to me, that's an artificial trigger, because it's not a response to some natural occurrence. If you ever execute a pipeline from an external source, like we're going to do today via Logic Apps, that will register in the Data Factory system as a manual trigger. So what we actually end up with at the end of this queuing system is we do not rely on natural triggers within Data Factory itself. All of our Data Factory triggers are going to end up being manual or artificial triggers because what we are trying to accomplish from an architectural standpoint is to decouple the event of requesting the execution from the actual execution. And a quick scenario of why that's important. We may have, let's say you have a daily process that runs, every night at 2 a.m. If you relied on the Data Factory trigger to handle that scheduled event, when that fails, and maybe you don't discover it for 3 days. When that fails, how do you go back and run that trigger again, right? And then the short answer is you really can't. You can go and within the monitor of the Data Factory, you can go and rerun that pipeline. You can rerun that effort. But if your design is such that, again, back to designing pipelines in isolation, is designed to where it's going to run based off of the system clock, you've now lost the opportunity for that previous scheduled run. So you have to architect a way around that. And one of the ways that we do that, and I should have added a bullet point to my pipelines, is that we rely heavily on parameters. So we design our scheduled-based pipelines to accept parameters to define those dates rather than relying on the system clock, rather than relying on, again, the natural scheduled trigger. And again, these are just lessons learned from years of dealing with these kinds of systems. So by removing that or decoupling the actual request for the work from the work itself, we actually end up with a lot of flexibility to rerun jobs that failed, or maybe the trigger failed. Maybe for some reason it didn't actually pick up. Well, we can go in and manually add that to the queue and force the job to run again. Or we can even create future jobs. We can put things in the queue that have these parameters for other, for triggers that haven't occurred yet. So there's a lot of benefit, again, to separating the trigger from the pipeline execution, and that's why at the end of the day, all of our triggers are manual triggers. So this finally leads us to a queue. So if I'm going to have everything triggered manually by an external process, so I've taken Data Factory out of the trigger business, that's where a queue comes into play. And I'm using a very generic sense of the word queue. This is not literally like an Azure queue or some queue product or something like that. Again, conceptually, that's up to you, however you want to implement that. When we were putting this together, it was very piecemeal, and we were just trying to solve some of these problems that we were having. I just picked an Azure SQL database. So the examples that you see today are going to be based on an Azure SQL database whose entire function is to service the queue. So it's a handful of tables which we're going to look at. It's a handful of stored procedures which we're going to look at, and it's just a very old school, straightforward approach to what is relatively small amount of information. But again, it fits very nicely into Logic Apps and even into Data Factory and other bits and pieces. And you probably already know how to do everything that you're going to see when it comes to actually dealing with the SQL Server itself. So that's the decision that I made. Again, feel free to take this concept and implement it in Cosmos or something else if you really want to. But I've been very satisfied with this over the last couple of years. And in this Data Factory, we're going to define a pipeline, a job, a pipeline, and Data Factory itself. And then we're going to leverage the data that's in that database. This also, by the way, gives me very easy ways to manage and input and work with the data that's in the queue itself. So internally, we have a website that I've built that that its whole job is to manage this database, and that also means that some of our other folks who are not necessarily technically proficient, they can just go in and add new jobs if they need to, or monitor the process of another, the status of another job. So again, just a really simple, straightforward, but repeatable approach to solving this problem. So every pipeline run is defined by a job configuration, and that job configuration has a relationship to a data factory entry. So we actually ended up with multiple data factories. So we don't rely on a single data factory for all of our work. We have so many pipelines that we've broken those out into multiple data factories. Each data factory has many pipelines. And so this gives us also a unified way to work with multiple and many data factories. When we finally get down to it, where we're processing the queue and we're ready to execute a job, every one of those is a manual trigger, right? It's going to pull that job out of the queue and it's going to submit it for execution to the data factory. So that's the high level stuff. Let's get into a few of the actual implementation details. We're looking here at the simple diagram of the tables that I was just discussing, and we have the data factory job, and the reason that we or table rather, I'm sorry, the reason that we have that is because when we get to the actual execution, the actual requesting of the job, there are certain things that are required to make that happen. That is, we have to know the data factory name, we have to know the resource group, and we have to know the subscription name. And it is a subscription name, not the subscription ID. So if you change your subscription name, which does occur once in a while, and you've set this up, don't forget to go back in here and change that. Another lesson learned for you. And then that data factory is referenced by a collection of pipeline jobs. And this pipeline job is the configuration of the pipeline. So you'll see here that we have the pipeline is the pipeline name, the actual name of the pipeline within the data factory that we want to execute. These parameters, and this is, there's certainly room for improvement. We have not found yet where we needed to go beyond 4 parameters, but if you're in that scenario, the next iteration of this for me would be to break those parameters out into another table so that I wasn't hard coding a certain number of parameters. That's in, but this parameter piece was what originally drove us to this design, and we'll talk. I'll try to remember to talk a little bit more about that when we get to the logic app that wraps this and does the actual execution, and explain why it's defined this way. But in the pipeline job table, this is the name of the parameter. So this is the name of the parameter that the data factory pipeline defines. And it turns out when you call a data factory externally, you can pass parameters that are not defined, but you cannot not pass a parameter that is defined. So this becomes a mapping of defined parameter names to, when we get to the actual queue, this is an execution queue, this is the parameter value. So this parameter 1 value has to line up with this parameter 1 name. And so that's another area where this could be improved would be to break that parameter information out into another table or two. But at the moment, this has been very successful for us. And again, sort of a low-tech way of handling this. And then another item that we are going to specifically address later is concurrent pipelines. So one of the strengths of Data Factory is the ability to run jobs in parallel. While most of our jobs, just because of their very large batch-natured workloads, and also the sync is an Azure SQL data warehouse for most of our work. Some of the architectural decisions in those table designs make it smarter for us to do one pipeline at a time. However, we have many jobs that they can run 3, 4, even 8 pipelines concurrently. And the way that we leverage that is through this current pipelines column. So we can define at the configuration level how much concurrency does this workload, does this pipeline configuration permit, and then that is later handled on in the queuing system. But so that's a really interesting element as well that helped our performance in the early days. And then finally, just to reiterate, so pipeline job and data factory are configuration tables. Pipeline queue is in fact the instance table. So each row in pipeline queue represents an actual pipeline run that either needs to occur or has occurred. So just very quickly to give you a flavor of what the data is like, obviously for security reasons, I'm not sharing our subscription names, but we do have, again, at the data factory level, we have multiple, and there are more data factories in our production instance, but we have some data factories defined here, and rather than having to input this data over and over again in every instance request or even every job pipeline job row, we just used a standard referred tables, a standard related table here to handle that. I also want to talk about the status feature real quick. You'll notice that we have status in every one of these tables. So we have a very high level of control over whether or not a data factory is active. So if we came down tomorrow and said, you know what, there's something wrong, or we have some licensing issues or something of that nature, I don't want to run this gold standard matching. I don't want to run any jobs in that data factory right now, because again, remember, we have designed our data factories to be task or group oriented. I can actually shut down all of the activity by simply changing this status, and we typically use active and paused are our two primary statuses. So I can pause an entire data factory, or I can pause an entire pipeline job. So the data factory is still active, but within it, these two jobs at the top are paused. So this is also really interesting because it allows me to continue to queue jobs. So if I have queue jobs that are based off of, again, maybe natural triggers or something of that nature, and this pause is just temporary, I don't have to lose the fact that those jobs need to be run. So they still get written to the queue. They're still in a waiting state, but they won't run if the data factory is paused. So when I'm doing significant updates to an existing pipeline, I will go in and turn the pipeline to paused. Maybe it takes me a couple days to get through all of those and get through my testing. And maybe I don't want to be running them while I'm working on it or something of that nature. Obviously, that's not terribly sophisticated. We can get away with that in a small shop. If you're in a large shop, then you're going to be leveraging some of the CI/CD kind of stuff that Andy was talking about in the previous session. But it does give me a lot of control. So again, here we are looking at a pipeline job, and we get to see what that data looks like. And there's some samples here of what a parameter name might be. I don't actually know for certain whether or not these are case sensitive. So personally, I always err on the side of caution and I treat them as case sensitive. So if we were to go to this actual pipeline in Data Factory, we would see that it has two parameters defined. One is named state and one is named data source type with that exact casing. And then again, this is the configuration of the pipeline. And when we get to the queue, those values are then registered. And unfortunately, I don't have any waiting jobs because this is all actually based off of production data, and our pipeline keeps everything running. So I don't have anywhere a job is waiting to execute that I can show you, because they almost all get picked up immediately and run. But that run ID, based on what you're going to see later, would actually be null because that run hasn't executed or started yet. And then the status is also null. That's another change that I would make if I was redesigning this today. I should not have relied on a null status. I should have relied on something like a ready status or a waiting status or a queued status, something with an actual value. But again, it works. It's fine. So a null status and a null run ID indicates a job that is ready to go, that needs to be executed. But that status, once again, I now can go all the way down to the individual run, and I can say, you know what, I don't want that to run. So I can set it to any status other than null, and it will not be picked up by the queue system. So that's so again, a very granular, all the way from a really high level all the way down to a really granular level of control over the jobs that are running in the queue or need to be run in the queue.
Hey, Joel.
Yes.
We have a question here.
Okay.
From Dean. Is there any logic or table to maintain the inter-pipeline jobs dependency to address use case like, let's say, pipeline X should start once pipeline Y is successfully completed?
That is a fantastic question. So I don't have that built out yet, but it's actually I'm actively working on that because it turns out, it is a slightly more complicated problem. It's a little straightforward to say when pipeline A finishes, run pipeline B. But what we run into in reality is that we run groups of pipelines. So this particular, if we go back a screen, right, this particular ingestion pipeline, when that comes in to run in our system, there might be 17 of those, there might be 50 of those. And what I really need is I need all of them to finish. Right, so it's like a queue. I need that entire queue to finish, and then I want to execute the next pipeline. So in that scenario, it becomes registering a queue of queues, and so that's actually a project that I'm currently working on to solve one of these related issues where we have exactly that scenario. What I do in the meantime is I allow, like say that's not the case, and when this ingestion, when this ingestion job finishes, I want to run this upsert job. So I would call that a dependent pipeline. What I will actually do is I will, if there's not a natural trigger that solves the problem, I will simply have this pipeline, when it gets to the end, that I have its last activity be to queue the next pipeline that needs to run. So inserting to our queue table, the next table here, I have a stored procedure for that, and I have many different places, both logic apps and data factories and our website, that leverage that stored procedure to queue a job. So if you really have dependent pipelines, rather than having the system maintain it, you simply have a pipeline queue another job, and then if that job, when it finishes, if there's another dependent job, it can queue the next job. And so we're constantly sending requests back to the queue and relying on the queue system to pick those up and execute them. But that's an excellent question, and definitely something that I'm currently working on. Okay, so let's move forward. So to manage these tables and to manage the actual queue, we have two logic apps, and this is broken down into at a high level, logic app number one is process the queue. And so logic app number one's job is to find out whether or not there are any jobs that should be run. And so the way that we do that, and we run that every 3 minutes. So every 3 minutes, this logic app runs. We used to do it at 5 minutes. We bumped it up to 3. Just so we could actually have a slight, because there's a little bit of lag, that 5 minutes creates a little bit of lag time. And so cutting it down to 3 minutes means that our jobs get picked up just a little bit faster. And so every 3 minutes, we call a stored procedure. And it returns a list of active jobs. So if we went back to this pipeline job, it finds all of the ones that currently have an active status, and it joins in the data factory data that it needs. And so it returns that list back to the logic app. And then the logic app, and by the way, here's the stored procedure. So this code is all in the slide deck. So when you download the slide deck, if you want to try and implement this, almost all of the code that you need to do will be there. And in this case, you'll see where we're joining to the data factory to pull those elements that I said we need at request time, which is the resource group, the subscription name, the pipeline name, the data factory name. But we're basing it off of where the data factory is active and where the pipeline job configuration is active. So that gives us back a list of active job configurations. And then for each job configuration, we call another stored procedure that says, get me the next job run. Now, if there are none, like I said, these get picked up and run pretty quickly. If there are none, it simply won't, there's nothing to return, right? It'll return a -1. But if there is one, then it returns that information and we proceed from there. Now, this stored procedure is a little more interesting because it also handles our concurrency. So we're allowing that all to be handled by the SQL engine, and we pass in the job ID, which we got from the previous stored procedure. Remember, we're looping over this list. We pass that job ID in, and then everything else is an output parameter. And we check, and we're relying on the status. So that status field becomes super important, but we're relying on the status field inside the pipeline queue table. And we're getting, so first we grab how many concurrent pipelines are allowed. We grab that from the job configuration, and then we say how many are in progress for that, for that job configuration. And then we just compare those numbers. So if there are any that are waiting, that are ready to go, and if the total that is currently active is less than the number that we're allowed to have, then we return the next one on the queue. If those things all fail, so if there are none waiting, or if we're already maxed out on our concurrency, again, whether that's 1 or 5 or 10, then it returns -1. So this stored procedure is really kind of at the heart of the entire system because it decides whether or not a job is ready to run, and it returns that information to the logic app. And then if it is true, right? So in other words, if a record came back, and so this is also important to understand, even though we may have a concurrency of 5 or 6, and maybe there's none or 1 running, we only return 1 at a time. So we only return the next one that's available. And if we go back and remember that this is on a loop that runs every 3 minutes, it means that we're staggering our pipeline runs per pipeline. We're staggering the executions by about 3 minutes. And that actually turns out to be kind of nice as well, because rather than hitting these resources all at once, say you allow 10 concurrent jobs, rather than submitting 10 concurrent jobs all at once, you have just a staggered starting time. Which it sort of increases the throughput just a little bit, and it also allows that if something starts to break down, you can maybe catch it in the middle and you can pause that job where maybe you've only submitted 1 or 2 as opposed to all 10, where now I've got to go and handle the fact that all 10 of those need to be, reset and rerun, et cetera, et cetera. So that staggered approach, it also cuts down the amount of processing time that has to happen within the logic app itself. So understanding that this is running over a loop of job configurations, if I have a lot of parallelism and a lot of active job configurations, that could end up being more submissions at one time than Data Factory may support, or I may cause problems for myself if something's broken. So I like that staggered starting time, and that's effectively what this select top 1 permits us to accomplish. And then the last really important point here is that Logic Apps does have a built-in Data Factory connector. Now, when we started building this out, that wasn't true. That didn't exist, so we went down the road of creating a function app. So here's a function app, and we're taking those again. We've captured from our stored procedure that there's a queue job ready to run. We're taking that information and this coalesce bits here, that's what's doing the mapping for us based on the parameter name, and then we're sending this information in a JSON body to an Azure function, and then that Azure function actually handles the execution request. So originally, again, you couldn't execute Data Factory directly from Logic App, and then they added that. Pardon me. But for a short while, you could execute a Data Factory, but you couldn't pass parameters. So this still turned out to be beneficial. Well, today you can call from a Logic App, you can call a Data Factory, you can pass parameters. However, that Data Factory, you have to know it at design time in the Logic App. It's not a parameterizable activity. So I find that this Logic App is still the proper way to handle, or this function app rather, is still the proper way to handle it, because it allows the ultimate amount of flexibility. So now I can literally just go into my configuration system, add a new Data Factory, add a new pipeline, define the parameters, and this just picks it up and keeps running. I don't have to make any changes to the underlying Logic App. So let me try and pick up the pace just a little bit here, make sure that we get through all the material. This is the relevant code from the Data Factory execution from the function app itself. I do use some Key Vault access, which I have collapsed here for security purposes, obviously. But this Data Factory helper is a class that I wrote, and it is in the appendix of this slide deck. The entire class is there because we're going to use it for a couple different things. So just a quick caveat that when I wrote this Logic App and when I wrote the helper factory class, it was version 1. It was framework only. If you were going to go down that road today, I can't tell you whether or not it would be exactly the same with a .NET Core implementation against the Azure Functions 2. But again, the concept is where I would recommend that you go. Is that you use something outside of Logic Apps to handle the actual execution request. Now, if your scenario is really simple, where you only have and will only ever have a single Data Factory, then obviously, feel free to rely on those built-in tools. Okay, so now that we've executed the Data Factory pipeline, that function returns. We'll see here that it returns the run ID, which it got from the Data Factory SDK when it submitted the job. So we're going to take that run ID and we're going to write it back into our database, and that's how that value gets populated. And then we're going to leverage that run ID later in our next Logic App. So that's and then here's again just a super simple, straightforward stored procedure that we use to update that run ID. Okay, so now that we have the data elements in place and we have the Logic App that's leveraging the stored procedures and it's leveraging the function app and it's getting the Data Factory to execute, now we need something to keep that running. So if you think of it in terms of, when I execute a data factory, the data factory itself can't let me know that it finished. It can't do that directly because it's still running. And so you run into a chicken and an egg problem. So what we do instead is we have a second logic app that regularly pulls the status of the jobs. And effectively what it's saying is, grab that run ID for all those in progress jobs. It calls another Azure function that we're going to see that goes out to Data Factory using the SDK and checks the status, and then returns the status, and we update the status. So that logic app, that monitor pipeline status, it runs once a minute. Because it's much quicker. It calls another stored procedure that gets a list of all the in progress run IDs. So once again, that status field is really super important. This in progress label comes directly from Data Factory, as does succeeded and as does failed. So we go and we grab all of the run IDs that have an in progress status and a couple other columns. And then we pass those columns to a function app that uses the SDK that checks the status for us. And so again, the relevant parts of that function app are here. It's pretty straightforward. Get pipeline info async, which again is a method defined in that class that's at the bottom of this slide deck. And then it returns that status back to our logic app. But when we take the first thing we do with that status is we go and then we update the queue entry. So that's how it goes from in progress to, and I can tell you it's either going to be succeeded, canceled, or failed. Those are really the four options of statuses in a Data Factory pipeline. And whatever it is, it's going to update that status in the database. And again, we have another. We use that run ID status procedure to handle that. So we have another stored procedure. So again, we're just using really traditional methods, and we're working outside of our Data Factory to manage the Data Factory rather than relying on Data Factory to do all of the heavy lifting itself. So this is again what updates the status. And if you have 10 jobs that are waiting to run and one of them's in progress, and you got a concurrency of 1, now I come in, I look at that in progress, I go out to the Data Factory SDK, I find that job has succeeded, it comes back, and I update this value with succeeded. Now the first logic app, when it comes through its next 3-minute cycle, it's going to find, there are no more in progresses, but there are some waiting, and I have a concurrency greater than 0. Therefore, I'm going to go ahead and pick up the next one. And so these two logic apps work hand in hand to keep the wheels moving, to keep the queue processing. And then finally, now that we have all these tools at our disposal and we have a functioning queue management system, now it all comes down to registering jobs in the queue. There are, we mentioned earlier, but there are a number of different ways to do this. The one that I use the most is the stored procedure. So I actually don't have that in my example, but it's literally just an insert job where you pass the job ID and the parameters. And it literally just creates a row in that pipeline queue table. And once that occurs, all this other stuff that we've been talking about just happens, right? So because everything else is already running and these are all automated and in play, all I need to do now is get jobs into the queue. So we had an example recently where we literally had a machine learning project where we had to queue up 1,200, it's either 1,200 or 1,250 jobs, I don't remember. And we don't have any mechanism for that. So I literally wrote a console app that was based off of a couple other items that outputted the insert, the stored procedure calls, and I just ran that in SSMS, and it did a bulk insert of the data into the table, and so by getting that data into the table, all of a sudden the queue was populated and ready to go. So there are a number of different ways to do this. A website, an HTTP access of some kind, an API, a REST service, what have you. We do this again internally. We have a website that we use to manage our queue, and so that website just writes into the database. Events and scheduled logic apps. So I mentioned earlier this concept of separating the natural trigger from the actual execution. We have a lot of logic apps that run on a timer. Or on a schedule. And if you hang around Stack Overflow, you'll see questions come up frequently where someone says, hey, I want to schedule my this data factory pipeline. I want it to run every hour, but only between 9 and 5 Monday through Friday on the Eastern Standard Time Zone. That level of granularity doesn't exist in Data Factory. Data Factory itself can't handle that, at least not very easily. You have to become a real expert at pipeline execution language to be able to do that. But logic apps it's actually pretty simple to set up something of that nature. So we have several jobs that do things of that nature, and then that logic app's entire job is get to the point where it can call the stored procedure to insert a row into the queue. So we have a lot of logic apps whose whole job is to queue up jobs. And then again, you can also have that happen based on events. So a new blob trigger occurs, and it says, hey, there's a new blob here. Well, rather than having that blob event kick off the data factory, that blob event says, hey, I found this thing. I'm just going to go write this job to the queue. And my hands are free. And then finally, and this was the question that came up earlier, pipelines registering dependent pipelines. That's where the pipeline at the end of its functioning, the last activity, is to call that stored procedure and queue the next job that it knows is dependent. So obviously, this is not meant to be an exhaustive list, but we run into this kind of stuff all the time. And having this queuing system in place actually makes it really straightforward to get a whole lot of work done with very little effort. And with that, we are at the end of the presentation. Srini, do we have any other questions in the queue? See what I did there with the queue?
Yeah. No, you did a good job of answering that. I did paste a link to a inbuilt feature within Factory to create a tumbling window trigger dependencies. But AV, I don't know the full name, pointed out that a tumbling window trigger can depend on a maximum of 5 other triggers. So which is a very good point out. So otherwise, it's just a comment. But, we don't have any other questions. But great presentation. This is something that you have done to really augment and strengthen the features of Azure and take it to the next level.
Yep, and if we have just 30 seconds, I'm not going to go through the details, but just so folks, if you are interested in that Data Factory helper class, the last 2 slides in the slide deck contain the code for that. And again, that's based off of the Azure Management Data Factory SDK DLL. So if you do want to implement that logic app, I've added this helper class that has both of those methods in it. You'll see them here: run pipeline async and get pipeline info async.
Okay, so this is awesome. And if you don't have any further questions, what I'm going to do is I'm going to stop the recording. But you can always reach out to Joel offline. He has thankfully shared his email address. And a slide, as always, slides and recordings already provide the link for you to access.
Thanks, Srini, and thanks everyone for attending.